pleased to introduce now H.Wenzl from University of California, San Diego, who will speak on braids, dualities, and more subfactors.
Okay, thank you for the invitation here. It's a very great conference. And okay, so I met Vaughan Jones in 1983 when I was looking for a PhD advisor, and I think I hit the jackpot with him. And Wendy already on Monday said, "No, what Vaughan thought would be a good advisor has to do, accessible, good ideas, and help supporting the student." And of course, Vaughan did all of this. And I'm pretty sure that at least all the many students I met, they have Vaughan's, they'll have the same opinion about them. So yeah, it's really sad he's no longer here. Okay, so what I'm going to talk about here is essentially, okay, I state here the Markov property, and unfortunately, I mean, for topologists here, I will mostly use this for applications to algebraic problems. So, all right, so let's just see. So Vaughan's original approach to get knot invariance was just here the series of representation of the break group, compatible with a natural embedding, and a trace functional, so which satisfies the thing if I multiply a braid with n strands with the new generator sigma n, which crosses the n and n plus first strand, then it has this multiplicative property. Okay, so before getting to this, how this works, let's just recall a very old fact, sure duality. And so this would be a special case where we have the symmetric group. So we take the n-dimensional representation of GLN, we let it act on the n-fold tensor product, then we know that the commuting algebra is generated by the symmetric group with the obvious action on the tensor factors, permuting the factors. And so hence one can, instead of studying modules of V, we can consider projections of CSN, which is the Carubian construction, to study representations of GLN. Now, of course, there exists now the Drinfeld-Jimbo quantum groups, which are Q deformation of the universal enveloping algebra, of a semi-simple Lie algebra. And so this is no longer co-commutative, but instead we get a representation of the break group on V tensor n. So of course, the break group is much richer than the symmetric group, so you could just ask now, for which representation V of U q G do we have analogs of the Schur duality? So that means that the break group generates the commutant. All right, I mean, that's a pretty simple question, and let's see. No, it is always by definition. It's of a quasi-triangular Hopf algebra. It has to be in the commutant, the break group, but it generates the whole commutant. So I don't know why it doesn't move to the next page now. What? Oh, okay. Thanks. All right, so here is a little table where, at least as far as what I know, and so for the first 3 lines, these are kind of, well, okay, let's look at the first 2 lines. This is, for SUN, of course, we get a braid representation which satisfies the Hecke algebra relations, and this has been known, I think, since Jimbo for a very old paper. And in the other case, for ON and SBN, we get another quotient of the braid, of the group algebra of the break group. I guess you should now call the Bmw algebra. And again, I think, I don't know, this has also been shown ancient, maybe Reshetichin wrote a paper where it appeared, or this has been known. Now for SO2, okay, it's if we take now the special orthogonal group, then we need an additional generator, and it basically comes here from this map where we can, so for a 2k dimensional vector space, we have a map from the k antisymmetrization to itself, and this map still commutes with the SON action, but not with the ON action. So we get an additional generator. So the break group alone won't do it. Then for G2, that's again, one can show that the break group is enough. For E6, E7, one can show that one needs again an additional generator. And if you look at it, this appears in V tensor 5 for E6 and V tensor 6 for E7. And that basically can be shown because there's an obvious, the SO10 is an obvious subalgebra of E6. And essentially, this F here, this new F here comes essentially from the F of SO10. But I keep it at this vague level here. But well, essentially, this 27-dimensional representation contains the vector representation of SO2k as a sub-representation. And then somehow from this one can show the existence of this additional generator. All right, so that's, and yeah, for F4, for E8, you get definitely another additional generator in the 7th tensor power, but there may be more, and yeah, I haven't looked at this, so because I may come back to this at some point. All right, so that's, okay, as I said here, this is again already what I said here. In the classical types, this has been known for a long time. And yeah, so how does one describe these braid representations in the exceptional types? Essentially, I think it's very hard to describe this via generalizing relations. At least I don't know any good way how to do it. So the one word description which one can do is you can define something called a path basis for n V tensor n, which would be a generalization of the Young tableau in type A. And then there exists a procedure called the choose-Murphy's elements, where you can calculate the matrix coefficients, and they're essentially unique functions in terms of Q. And so that's, and then one can read off from this coefficients of Q, one can derive this function. So that would be a rough outline of this description. All right, now, actually, okay, spin representation. Okay, there's a misprint here. Of course, there should be a spin of 2k plus 1 and not S of 2k plus 1. So this case was not listed above. And so one of the problems here is if you tensor the, and there's another misprint. So it should be the second tensor power of this is a direct sum of all the antisymmetrizations from the 0 until k. So you see that here the number of summands grows with a rank, and in particular one sees that the R matrix, the image of the break group, has k plus 1 distinct eigenvalues. I mean, this is comparatively easy to check then. And so it's very hard. So scaling relations would be very complicated. So, and there's probably no nice way how to describe it via scaling relations. There's one way how to describe this. One can use an auxiliary algebra, UQ prime SON. So this is another Q deformation of the universal enveloping algebra of SON. I mean, here are the relations. So you already see somehow R2 is similar like this braid things. The commute if it's the indices differ by more than 2. And there's this relation here. And to see that this is a Q deformation of SO2n, you just look at the following matrices here. You have here some diagonal block like this, 0, 1, negative 1. And you say di is then the block embedded on the ith and I plus first diagonal block. And then it's really easy to check this di's generate SON as a Lie algebra. And they satisfy this relation here for Q equals 1. So it's so we can view this as a Q deformation. And so what's the point of this? So one can prove, essentially, we can replace the R matrix by a matrix C, which lives again, I misprint. So here, this should be S tensor 2. So it's, so we replace the R matrix by a matrix C, and then embedded here in the n-fold tensor product in the usual way. We let this act on the ith and I plus first tensor factor. And then one can show that these guys generate the commutant of the action of the quantum group on the spinor representations. All right. So, and why is this helpful? Because these algebras, they are deformation for Lie algebras, so one can study the representation theory via using Lie theory, and at least if it is in the odd case, one can show that this decomposes into a direct sum of representations, which are deformation of representations of S or N. And so, if it is, and so this can be used. There are some applications here. Then you can deduce from this explicit calculations for the R matrix, or there are some other applications. If it's odd dimensional, then one actually gets some more interesting representations which cannot be obtained from deformations of classical ones, but it's essentially the same, is true. And in this theorem, it can be considered a refinement of skew-Howe duality for orthogonal quantum groups. And there's so it's sort of an analog, if you wish, of a paper by Kaminka, and Morrison, who did this for type A. But in type A, actually, both the original quantum group and the commutant is the same quantum group, while here you need a different quantum group. All right, so this is, in some sense, was just a little review. So now what is this good for? Well, okay, one thing, this is sort of classical stuff, at least in this first cases, like type A, B, C, using this Braid representation. I mean, okay, I'm oversimplifying this thing, but this approach, having some algebraic description of the commutant, then can be used to construct fusion tensor categories, modular tensor categories, which are important in Lie theory. Like, and here are some of the, like, of course, Christian and Rudis and Christianana, they did a lot of work in that direction. Another is what you could call categorification of fusion rules. The problem is, if I have an abstract tensor category, sufficiently nice, which is semi-simple, and has the same fusion rule as a compact Lie group, what can it be? And I mean, now this has been worked out now for the groups which I wrote down here. Also, I mean, some of them still has to be written up. And so let the G be one of those groups, and let C be a semi-simple complex linear ribbon tensor category, as I wrote here. Then the tensor category is completely determined by a number Q, which is not allowed to be a root of unity, and an element in a three-cohomology group of the center. And so in some sense, it's, and one can say what it is. If it's the trivial element here, then it's just the quantum group tensor category. So in some sense, you don't really get anything new, which is. And if GK is, well, okay, actually, I think I wrote it twice. Okay, forget about part B, I write about this again. So I talk about this again. So again, I mean, so where does this 3 cocycle come from? It's actually pretty easy for people who know about this. So the center is a finite group, and it induces and again I misprint here, a Z gradation of the rep G. Sorry, this should be a Z gradation. It's like, for instance, for SUN, center is Z mod n. So it induces a correlation with Z mod n. Like for instance, if you use Young diagrams, it would just be the number of boxes in your Young diagram mod n would be given this equation. And then basically you can twist the associated morphisms via a 3 cocycle of this group. So it's kind of a simple construction.
So this question, this term is very special for just these given groups like a Bmw, any fusion rule. There's no
well, yes, of course. I mean, that's okay. So there was asked, what about other tensor categories? I mean, I think this can be a very difficult problem. It really depends on the fusion rules. There may be none. There may be uncountably. I mean, yeah, this is very. It seems this. I mean, I wished I actually understood why. I wished I understood why the result seems to be the same for all compact Lie groups. I had a conceptual way how to do it, but I don't. So. Anyway, so this started a long time ago with a paper with Kashdan, and then I did it with some former PhD student of mine for some other types. Then a current PhD student did this. Okay, what did I do now? Sorry. Where are we here? So, no. What am I doing here? So how do I how? Because I think if I push this now, I don't. Let me see. Okay, good. So we're back. Yeah. Anyway, so this done. So basically, so the SU and ON and SO2N, they have been done, and for SpinN and for G2, this hopefully will be written up over the summer. So it's. All right, now as I talked about, this Vaughan's Markov property plays a role here, because I remember at some point when I was visiting Harvard, and actually David Kashdan gave a lecture where he proved the result for SU2, and then I didn't know anything about categories, but I thought this can be generalized for Hecke algebras, and his first question was, how do you know that the representation of the Hecke algebra gives you exactly what you need? I mean, it gives you the correct quotient. And essentially, one can use this argument which I sketched here. I mean, there exists a natural category, dimensional tensor category, and a representation of the Braid group into this, which factors over the Hecke algebra. Now, this trace function satisfies this Markov property, which is an easy consequence taking partial traces. And so, and those Markov traces can be easily classified, and then, so hence, one can show them this, that it has to be the correct thing, using rigidity of a category. But, I mean, it's a vague outline, but I just want to make the point here that one of Vaughan's ideas proved useful also here in this context. And yeah, so I mean, in those times, I mean, one of the reasons for this was there are lots of different ways how to construct fusion tensor categories, which I'll come to at the next slide. And so at least this provides an easy way how to check that you get the same thing for all these different ones. And also, more recently, this was actually last week in Terry Gannon, who already was mentioned in David Evans' talk, who works on studies vertex operator algebras. He tells me that this is useful for his thing. So, all right. So, yeah, I don't know. Very briefly, fusion categories that have already been mentioned before, so I don't know how much I should say about it. It's so if you look here at this graph, this describes the tensor product rules for SU2, where 1 would correspond to the two-dimensional representation, and then basically tensor product rules are given if I dot like 3 with a vector representation, then it's a direct sum of the adjacent dots. So that's the usual tensor product rule for SU2 here. And then one can show there exists a smaller tensor category where you basically, instead of this infinite graph, you have a finite graph with this, and the tensor product rules are analogous. So, and this can be realized, for instance, for a quantum group SL2 at an Lth root of unity. And so then, and essentially the same proof which was used before for the arbitrary Lie group here in part A, here, will also go through for this fusion case here. So, except now, instead of saying that Q was not allowed to be a root of unity in the theorem on the previous page, now Q has to be a primitive Lth root of unity. So that's all right. So that's, I think, all I wanted to say about this tensor product. Okay, now, as a conference in honor of Vaughan, so one should probably say a little bit about subfactors. Already Dietmar and David said something. So maybe very briefly, okay, here a type 2-1 factor, it's an algebra of bounded operators closed under the star operation, closed under the topology of pointwise convergence, so that's described here. And factor means just the center of the algebra is trivial, only multiples of the identity. And type 2-1 means it's infinite dimensional, but it still has a finite trace. So functional which satisfies these things. Okay, and so of course Vaughan here starts inclusion or n or m of factors. So and in particular he defined an index, which I'm not going to give here. But, and I think the original examples in those times were just given, say you have H in G groups, say finite groups, acting via outer automorphisms on the type 2-1 factor. Then let M G be the fixed points under this, and MH, of course, the analogous fixed points. Then this index is given by the index of the subgroup. And that was Vaughan's reason to call this an index for subfactors. So. And now the index alone usually doesn't, almost never classifies the inclusion. There exists an additional invariant, or several additional invariants. Another one is, which they call the principal graph, which can be explained by induction restriction rules of bimodules, but I don't think we need this here. For our example here, this is just given by the induction restriction graph between a representation of G and a representation of H. So it's a pretty natural invariant. So this was one of the standard examples. Another one you can get via G modules. So let V be a G module, usually finite dimensional. So then what we can look at, if you look at the right-hand side, we can embed one tensor, the G intertwiners on the n-1 times tensor product of V into this whole thing. So we get a sub-algebra into an algebra. And then if we can let now the limit go to infinity, take the closure under this topology, and we get a subfactor. And this subfactor has indexed the dimension of V squared. All right. So in this times, I think even Vaughan at one point told me that when he started with this, some people thought that's probably all you will get as examples, which of course is not true. So one can now, for instance, one has a Q deformation of this essentially by using quantum groups. You can just replace V by a representative of the quantum group, and then one gets a subfactor by a similar construction as here, whose index is, let me just see, I think this is a little, yeah, okay, so whose index is given here by the Q dimension of quantum groups. So I'm not going to give the formula. It's like, for instance, for the vector representation of SLN, it's just the Q number. For SLN, it's this Q number plus 1. And now, for if G is equal to SL2 and B is C2, then one obtains the original Jones subfactors of index 4 cos squared pi over L. So, and of course, that was Jones' big theorem was if the index is less than 4, then it has to be one of those numbers. So that's important. So at least if you look at this, for example 2, we have a rich Q-deformation structure. So here the indices are obviously not integers. And so you have a nice sort of generalization. So what I'm going to talk now next is the question, can we have sort of similar Q deformations in this setting here, group, subgroup? So, now this leads now to oh, okay. Oh, okay, sorry. Yeah, to motivate the notion of a module category. And again, this is informal. It's just, I wrote it down there, but it's kind of the obvious thing. I mean, at least in this informal setting, you have an abelian, if C is a tensor carry, M is an abelian category, and it's called a module carry if you have a functor M cross C to M, which should satisfy usual associativity properties. Okay, so then an easy example is the following. If H and G are groups, then rep H is a model category of rep G with a model action given by a restriction. So it's kind of a triviality. You can tensor a representation of rep H with a representation of rep G by just using the restriction functor to make V an H module, and then you just take the tensor product of H module. Okay, so and for groups, this is basically all there is, modulo some twisting via cocycles. So what about the module carriers of these fusion categories, which I mentioned before? Now there exists this. So again, FGL is just what I did before for SL2, where you can restrict this tensor carrier only having finitely many objects at the root of unity. This can be done for any Lie type. And so we have this fusion categories. And so can we find subgroups where we can pull this module category up here to the level of fusion categories? And this is really a tricky question because, for instance, it's known that in general, if you have a subgroup H and G of Lie algebras, then this doesn't carry over to the corresponding quantum groups. So it's all right. Now, what about known results? So the first one is already way back, Goodman, de la Harpe, Jones, in a time when this notion of module category didn't exist. So we have this here. And essentially, we have also, what already Cameron showed, we also have an ADE classification here. So if you take SO2L, I think this time it's actually slightly smaller SO3L one. Then there exists a module category M for each graph of norm 2 cos pi over L. So these are, so if L, you always get AL, and I think for L, yeah, I forgot now, even or odd, that you get also a type D one, and for 3, I think for 12, 18th, and 30th root of unity, you get E6, E7, and E8. So we have here sort of two, which one calls non-exceptional ones, and 3 exceptional module categories. So this is essentially the result for SL2L. So now, what about other types? Oh, well, sorry, I completely messed this up, but okay. Yeah, so for SL3, also that was obtained by work for a lot of people, a similar classification can also be given for SL3. There exists, again, 3 exceptional ones and 2 series of non-exceptional ones. All right. All right. So, but in general, like I think there were also some announcements by Ognana for SL4, but it got more and more complicated. And I think it still is. But so here now comes my rather naive idea, what I said before. So, can we construct modular categories by using proper Lie subgroups? And yeah, and so this is possible if we take SON into SLN, and if n even also for SPN into SLN. So for n equals 2, this would be the Goodman-Delap-Jones subfactors, and you would get some index of this form. And for L equals 3, well, okay, so I wrote down here some formula, which I don't think is that important. Also, one can describe essentially the principal graph by, essentially they are given by restriction rules from SU3 into SO3, where now we have to restrict it to this finally many representation in the fusion category. And this can be comparatively easily adjusted because one has formulas for the dimensions of these objects. And so it's not that hard to figure this out. But basically, if the representations are close enough to the trivial one, then it would be the classical restriction rules. And then if you get closer to the boundary of this finally many, then you have to make some adjustments. And now this formula actually only works for L odd, and for L even, one needs a slightly different formula. But we'll get back to this. And it seems there was some construction via loop groups which produces the same thing, but it's usually very hard in this loop group setting to do any calculations because you have to deal with infinite dimensional spaces. All right, so now what about so these are the examples for SU3, and then, yeah, okay, maybe I just go very briefly on this. I don't think the formulas are that important. So if you have, if in a general case, you can always write SLN as SON plus an additional representation, as in these cases. And then you can get some general formulas for the index by using representation theory, which, I mean, are not, anyway, so basically, I mean, if you know about the formula for the dimension of the fusion category, this formula would be essentially this product here over all positive roots and L over the rank. And now here for this sort of index, you only basically allow this product over roots which are not in the SON, and also L, the power, is just the difference of the two ranks. So NP is the difference of the rank of the big one minus the smaller one. Anyway, the point is one can give some pretty precise information. And also, again, this principal graph is given via this restriction rules. Okay, so that was it. So now, how does one do this? I mean, how does one construct this? So essentially, okay, so we start out with the original embedding here. So n SUN into n SLN. Now, as we know, by sure duality, we know that this is given by a representation of the symmetric group. And this one, by a classical result, is given by Brouwer's centralized algebra. And Brouwer's centralized algebra has a basis given essentially by you represent permutations via permutation graphs in the obvious way, and you add this additional generator. And multiplication is given like with braids. You put them on top of each other, and when you have some disconnected loops, you pull them out and multiply this whole thing by n. So it's a simple one. Okay, so we know what's going on in the classical case. So now we want to get the Q deformation of this. Now this case is pretty clear. We know then we get the Hecke algebra. So we only need to know essentially how do I define the relations involving this guy here. And now the one relation G1 equals QE, that's pretty easy to see that this is the only thing which makes sense. And so essentially, the critical thing is how does this element commute with the sigma 2, like when you have crossings of the second and third strand. And here now again, Vaughan's Markov property comes in, because we want, in order for this to work, an analog of this Markov property has to hold. So again, we have this kind of product formula. And using this, you get certain relations on the structure coefficients, and it turns out that this is enough to pin down the thing. And anyway, I mean, I wrote down the relation, but I'm not sure how. I'm sorry, I'm still bad to drawing pictures on my files, so it would be probably easier to see this via pictures. So, I mean, I wrote down the relations down there. And maybe let me make some comments about this. So one can use sort of graphical calculus to motivate some of those relations. Unfortunately, they do not always correspond to topological things. So like I mean, if you try, of course, it would be tempting just to use this as a cap graph here, I mean, as a rectangle, and use the simple reflection via braid generators. And so if you do it by pictures, then of course you would get certain graphs in like braids. And if it would be nice if this would reflect the topological effects. But this is unfortunately not true. So in that sense, I don't know whether this will be used for anything in topology. So, I mean, some of them make sense, some of them not. But it's messy, so I can't really say that much. But, I mean, these algebras exist, and they do exactly what one wants to do, at least for constructing module categories and subfactors. So for that things, it works. Now, so this was actually already a while ago when these results were obtained. So the question was, is that all? Now, these were symmetric spaces, so at some point I was hoping that maybe one could get analogs of this for any symmetric space. And so I spent quite a bit of time, and it didn't work because it is not possible. And I'll say a little bit more about this in the rest. Finally, I got one subgroup where it did work, namely, if you embed SPn minus 1 into SUn for n odd, then the same thing, okay, I should say I think it works. I already did at least half of the work for the construction of this, which I had done in the other cases. And every indication is that this will work in general. And so then, assuming that this really is true, then one can have the following. If you have a subgroup H in SUn, and we can really get sort of a module category of the corresponding fusion tensor category, then H has to be either SON or SPn or SPn minus 1 if n is odd. So this is all you can get if you want to get sort of this analogs of subgroups in the fusion setting. And yeah, so of course the question is there some algebraic interpretation? And so in these first two cases, there exists actually this algebra UQ prime SON, which I mentioned before. Also, it can be embedded as a co-ideal algebra into UQ SLN. And so you actually have an algebraic realization of this for Q. But, and that actually made me look for, because this co-ideal algebras, which were defined by Letzter and what is it? I've forgotten, some Japanese people also. And, yeah, I thought it should work for other analogs of symmetric spaces, and as I said, it doesn't work. And on the other hand, this guy here, this embedding, doesn't seem to correspond to any of these co-ideal algebras, so this may be something new. All right, so, okay, so the last thing I want to say, why, okay, how do I know that there can't be more than this? And this is some stuff I should have looked at much earlier. So there's a way how to classify module categories by using the fact that the diffusion category for SU2 is a modular tensor category. So it means it has a representation of SL2Z. And so there's then a theorem which says, let's see, again. Okay, so, sorry, I forgot to write here. I should put in here, assume curly M is a modular tensor category. Then there exists a canonical matrix M with non-negative integer entries which commutes with this representation, called the modular invariant. So again, any modular category defines a modular invariant. And these modular invariants can be sort of, classified. So now, quite recently now, so abstract existence results have been obtained by Eddie Mitchell for all good modular invariants. Which, unfortunately, this doesn't really tell us what these guys look like. So, and one of the problem cases is what's called charge conjugation. Namely, basically, if lambda is a label of an irreducible representation in your fusion category, you map it to lambda bar. This defines a matrix in your representation, and this usually commutes with SL2Z. And so this is quite easy to write down, but describing this corresponding model category is actually quite tricky. And now, the examples which I constructed before are actually not exactly those, what I wrote here. And the expected difference can be easily described of the corresponding subfactors, which one can construct from this. So we have a principal graph, and which is given by this induction restriction graph. But for my examples, this is only the induction restriction graph from SUN into PSUN. So it's kind of a smaller graph. While the principal graph for the expected charge conjugation should be embedding for SUN into everything. So, all right. Now, yeah, maybe last thing is about this. So, as I said, there exists now some classification, namely, essentially one can show the following. So let C be the fusion tensor category for SLN. Then the module categories of C are classified by non-exceptional modular matrices, which appear for all L, and exceptional modular invariants, which only appear for finally many L. So the non-exceptional ones are given by charge conjugation, and by another symmetry, which is given by an action of the center of SCN, with something called orbifolds. So for people who are familiar, like for instance for SU3, you can arrange this, the irreducible ones in form of a triangle, and then it would just be the rotation via 120 degrees. So because one has an embedding of the center into the category via invertible objects. So, and so basically, they're given via orbits via this invertible objects. All right. So I think that's unfortunately I had Eddie Mitchell as a postdoc in San Diego, and so I think we're working about it now, extending this construction to get all possible non-exceptional ones. There are only finitely many exceptional ones, so I think this would be a pretty nice result if we could give a kind of conceptual description of all this non-exceptional modular categories of SUN. And I think that's it, what I have to say. So, okay, thank you very much.
Was there a question or comments?
Yeah.
How different is dn from the Bmw algebra?
Well, it has the same dimension. It has in a generic case, the same decomposition into irreducibles. But the difference is that dn contains the Hecke algebra as a subalgebra, while the Bmw does not contain the Hecke algebra as a subalgebra. So
I thought it does contain it as a non-unital subalgebra. I thought. Right?
I mean, it contains the Hecke algebra as a quotient algebra. Bmw contains the Hecke algebra as a quotient algebra, but not as a subalgebra.
But I think Veliakova and Blanchet showed there's a non-unital algebra embedding.
Right, non-unital. Yeah. But it's non-unital. But here this is unital. Yeah.
Other question? So maybe I have one.
Yeah.
You are working in a semi-simple case, but if you take, for example, a root of unity in the algebraic case, and you replace the fundamental representation by its projective cover, do you know something about the commutant?
Projective cover. No, okay. So basically, the interesting cases are for pure root of unity. But we mod out by all the negligible morphisms.
Yeah,
so
my question is, if you do not mod out, do you know something?
No, but yeah.
Other question? So if not, let's thank Hans again.
Okay, thank you.